In section 812, we're going to look at the active, reactive, and apparent power relationship in three-phase circuits. This borrows from the things that we learned in chapter 7 when we first came to terms with the idea that there is reactive power in a circuit and there's active power in a circuit, and that when we sum those two types of power together, we derive the apparent power. We talked about a power triangle relationship. And so this is going to expand upon that and work in terms of a three-phase circuit. And then we'll take that equation that we just came up with and apply it here, where apparent power is equal to the square root of 3 times E times I. So as with 811, I think I'll use the textbook again to work through this with you. We begin with this familiar equation here. Now we're just going to call it 8.10, which shows us the relationship with our types of power that we are familiar with. The apparent power is equal to the active squared times the reactive squared. And then this is sort of, in terms of the power factor, sort of defined differently because, you know, it's still the cosine of the angle, okay? The cosine of the angle is equal to the power factor of the three-phase load, where this angle now is the angle between the line current and the line to neutral voltage. The line current and the line to neutral voltage. Okay, so it's sort of defined a little bit differently than we had used before. This is the total apparent power in volt amps. This is the total active power in watts, and this is the total reactive power in VAR, volt amps reactive. Okay, so now as we look at that, we go over to example 8.6. And it walks us through a problem that we can work. And we'll work through this together. And that's all there is to this particular section. It's so easy because we're just going to borrow this equation that we had from the earlier section. This equation, apparent power is equal to the square root of 3 times the effective line voltage times the effective line current. A three-phase motor is connected to a 440 volt line. It's drawing a line current of 5 amps, and the power factor of the motor is 80%. Calculate the following. What is the apparent power? What is the total active power? And the total reactive power absorbed by the machine? This is, of course, getting back to our power triangle type problems. And of course, it's really pretty straightforward now, isn't it? If I'm given the power and I'm given the line current, and luckily I didn't have to derive either one of those. So let me see if I can write this over here. So total apparent power, S square root of 3 times 440 volts times 5 amps. And when I multiply that out, I get 3.81 kVA. That's my total apparent power. Now, I also have an equation, cosine of the angle, and we know that current is between the current and the line to neutral voltage, is equal to active over apparent. I'm told that the cosine is 80% or 0.8. Active, I don't know, but I do know this is 3.81 kVA. And so to get that to where I need to be, I need to multiply to solve this for active power. I multiply 0.8 times 3.81, and I will come up with 3.05 kW. All right, so now I can draw my power triangle to where I know the active power, and that is going to be my x-axis, and it is 3.05. If I said volts, I meant watts, 3.05 kilowatts. I know that the apparent power is 3.81 kVA. And so what I don't know is the reactive power Q. That's what I'm trying to find out. I have an equation for that. It starts with this, and I apologize if I'm being too redundant for you, but I just kind of like to feed these back to you until you get used to having them and get them memorized. And I solve for Q. It ends up being S squared. What color are we in? Red. S squared minus P squared. That is 3.81 squared minus 3.05 squared. Solve that, and I come up with Q is 2.28 kVAR. 2.81 kVAR. Okay, so using all of these things that we've learned up to this point, you know, all the way back to chapter 7, power triangle, then incorporating some of the things that we've just learned in chapter 8 with our square root of 3 times effective line times effective line current, line voltage, line current. We come up with the power. And so, you know, we utilize those to solve this particular problem. Now, I think if we do another section, we're going to be well on our way here with this course. So let's look next at section 813.